let's start out with a recap of the Poisson probability distribution. Again, we're talking about discrete random variables. So the random variable that might follow a Poisson distribution is an integer value. Okay, it's typically some number of counts. We can't have 2.3 counts. We have to have an integer number of counts. And so that's what our random variable will generally be describing. Okay, so let's say we have y is equal to some number of occurrences. Okay, and the hallmark of a Poisson distribution is we have some rate of occurrences. Okay, lambda here is going to be what we call the rate of occurrences. Some number of occurrences per interval, some interval. Okay, this can be a non-integer value because this is an average, let me say that, an average number of occurrences. Okay, the interval could be time, for example. This often deals with time. So the number of arrivals to a restaurant in the next 3 hours or something like that. Okay, this could be length. So this is the number of defects in the next few meters of cable, or something along those lines. We have some number of occurrences on average per some interval. If you see this kind of narrative written in a problem, or if you understand that that's the kind of problem that you're describing, where you have some rate of occurrences per interval, then you're probably going to have a Poisson problem. Okay? And this lambda describes that rate of occurrence. So how do we turn this into something usable? What's the probability that this random variable y takes on a realization little y? Okay? If y is a Poisson random variable, the equation here is lambda to the y, e to the minus lambda divided by y factorial. Okay? And that is the Poisson distribution. Lambda to the y, e, this is the exponential, this is Euler's number, e to the negative lambda divided by y factorial. Okay? Pretty straightforward kind of probability distribution. One thing to remember is that y here is bounded at the lower bound at 0, just like the other distributions that we saw, but it has no upper bound. Okay? So whenever we were talking about a binomial distribution or a hypergeometric distribution, we were bounded on the upper side by the sample size that we collected. Okay? We could get no bigger than n. Here, we can see as many observations as possible. We could see a million, we could see 18 million. There is no upper bound on the random variable y. But it does have a lower bound at 0. We can't have a negative number of occurrences. Okay? So we do have, at fewest, 0 occurrences.